Hi students, welcome to my lectures, and I request you to please follow my lectures from the beginning because every lecture is connected. In today's part of the story, we are going to cover the topic called partial pressure. As chemical engineering thermodynamics is targeting the separation and reaction, especially if a reaction happens or separation happens, example in the gas phase or so, the partial pressure play a very important role, because the driving force for any separation or reaction to happen, the partial pressure is one of the important ingredient. In ideal cases, the partial pressure could be the driving force. As I discussed in the earlier lectures, for non-ideal cases, fugacity will be the driving force for the separation and the reaction. Let us discuss about the partial pressure in very simple terms. As if you see the definition, partial pressure of a species or component in the gas mixture, example if there is a gas mixture, is the pressure that species I would exert if it is alone occupied the mixture. If you feel the definition is a bit complicated, let me explain you in a very simple term. This is a gaseous mixture, take this as a gaseous mixture containing the molecules of A and B at a certain temperature T, and pressure of this particular mixture is P mix. For suppose, Ya and Yb are the mole fractions of gas A and B in this particular mixture. Partial pressure of A in this gas mixture is, it's very simple, remove the molecules of B from the container, and if you measure the pressure again, the pressure of only molecules of A is called the partial pressure of A. From the same container, if you remove the molecules of A, example, the remaining molecules is only B. So the pressure at this point of time the measured is the partial pressure of B. So if you remove the molecules of B, you get a partial pressure of A. If you remove the molecules of A, you get the partial pressure of B. So that is very simple sense. Partial pressure of a species or component in the gas mixture is the pressure that species I would exert if it alone occupied the volume. If A alone occupy this volume, then what is the pressure? Then that is a partial pressure of A. If B alone occupies the same volume, then the pressure exerted by the B is the partial pressure, because inside the mixture the contributions are from A as well as B. So the total pressure is the combination of two partial pressures. So that is why I have explicitly written T is the temperature of the temperature, and P is the total pressure, P mix is the total pressure, PA is the partial pressure of A, PB is the partial pressure of B, and my total pressure is the contribution from A and plus B, which is PA plus PB. So let us assume that whatever gas is present in this container is ideal gas. You know, ideal gas mixture follow ideal gas law. So what is PV equal to RT? P is the pressure, V is the molar volume, R is the universal gas constant, T is the temperature. That means every gas has to follow this rule. Okay, every ideal gas. So let us expand. If you know the ideal gas, what is the partial pressure of A? You can estimate. In this total pressure, what is the partial pressure of A is nothing but fraction of mole fraction of A multiplied with total pressure of the container, then you get the partial pressure of A. If the mole fraction of B multiplied by the total pressure, then you get the partial pressure of B. So PA is equal to Ya into P, where P equal to, from here the P is equal to RT by V. Okay, PA equal to Ya into P, where P equal to RT by VIG. IG is representing the ideal gas. PB is equal to YB into P, which is equal to YB into RT by VIG. Because if you club, what is the total pressure of the container? Partial pressure of A plus partial pressure of B will be the total pressure of this container. So P mix is equal to PA plus PB. What is PA? You can able to put this expression in place of PA, put this expression in place of PB, and separate out RT by VIG, which is common in both the expressions. Then you get it Ya plus YB. As you know, for the binary mixture case, there are two components. So fraction of A plus fraction of B equal to 1. So YA plus YB equal to 1, which is nothing but RT by VIG. That is, pressure of this mixture is nothing but RT by V, which is P. P is again comes from the ideal gas, because the pressure, whatever the mixture pressure will be the pressure estimated by the ideal gas. That is what we have to convey. So in summary, total pressure contribution is the summation of two component species present in the mixture by two components which are binary mixture. So now you know what is the partial pressure of A in this mixture and partial pressure of B in this mixture. Are these really the driving force for separation and reaction to happen? In reality, whatever even though the pressure is not the driving force. And what is the fugacity? Because anything that reaction or separation to happen, it is not because of the pressure, it is because of the fugacity. Okay, for non-ideal cases, okay, you have to measure the fugacity. That means instead of partial pressure of A and partial pressure of B, you need to take the fugacity of A and fugacity of B. Why the fugacity is coming in place? Because if two molecules are in the same container, they start interacting with each other. When they start interacting with each other, the nature of molecule A, it will lose because of the B. The nature of the molecule B will lose because of the A. So for reaction and separation, the partial pressure is no more the driving force. Now we have to count these interactions into picture. That interactions are nothing but the fugacity, which we are going to discuss in the detail. Then how to calculate? What is the fugacity of A in this mixture, which is responsible for the reaction and separation to happen? Fugacity of A in this mixture is represented by FA cap. Phi A, Ya, P. Here partial pressure is only Ya into P, whereas the fugacity of A is Phi A into Ya, P. What is this Phi A? Phi A is accounts for the fugacity coefficient. Non-ideality of the molecules and A and B is clubbed in this fugacity term. Okay, this Fa is called the fugacity of A, Phi A is called the fugacity coefficient of A. The caps comes, don't worry about that, we will discuss about the notation at the later cases. Only thing you need to observe is for the ideal cases, partial pressure is driving force, which can be calculated using this formula. For non-ideal cases, fugacity of the driving force, so you can estimate using fugacity coefficient into Ya into P. Similarly for the B, it is Yb into P, whereas fugacity coefficient of B is nothing but Phi B, Yb into P. So this Phi A and Phi B are called fugacity coefficients, which accounts for the non-ideality of the mixtures. If you come to the example, let us do a small example. Let us say there is a container which contains certain molecules of A and certain molecules of B, and the mole fraction of A is Ya, mole fraction of Y is Yb at a certain temperature T and P. So calculate what is the partial pressure of A in this mixture, what is the partial pressure of B in this mixture. And let us say we know from the, let us assume the ideal case. For the ideal case, the partial pressure of A can be calculated by Ya into P. Ya is given 0.3. Total pressure in this container is the 2 atmosphere. So 0.3 into 2, 0.6 atmosphere. Pb is nothing but mole fraction of B in this mixture into total pressure, which is 0.7 into 2, 1.4 atmospheres. Mark these numbers. That means in ideal cases, if any reaction or separation we are targeting in thermodynamics, the driving force for A is 0.6 and the driving force for B is 1.4. Let us see in non-ideal cases. Given, I have already given what is the fugacity coefficient of A, what is the fugacity coefficient B. The values are 0.7 and 0.9 respectively. Same container, 2 atmospheric is a total pressure in the container. Ya is also same, 0.3, Yb is equal to 0.7. Let us calculate the fugacities. That means the true driving force here in the container. Fa is equal to Phi A into Ya into P is nothing but 0.42 you get, and fugacity coefficient of B in this mixture is Phi B, Yb into P 1.26. Again I have marked the values. Imagine in ideal cases, the driving force is 0.6. The same mixture, if it behaves non-ideally, the driving force is 0.42, which has been reduced. Again, the driving force for B is 1.4 atmospheres, whereas the real driving force for B in non-ideal cases is 1.26. You can imagine the difference in those values because of this non-ideality term. Okay, that is why always you have to design a separator or reactor not based on ideal numbers, based on the real numbers. I mean ideal numbers, and these are real numbers. So here what the chemical engineer has to apply a sense, because if you design the reactors based on these ideal numbers, you won't get the purity or separation as you expected, because you have designed based on idealistic scenarios. Always you have to design the things based on the non-idealistic scenarios. Okay, I hope now you understand the partial pressure effects. Let us meet with the new lecture. Thank you.